Thus far, we've dealt primarily with energy, position, and linear momentum, and we've proposed operators for each of these. One other quantity that is important in classical mechanics, angular momentum, is also particularly important in quantum mechanics, especially for the hydrogen atom. In classical mechanics, anything that is spinning has angular momentum, including something like a moon orbiting round about a planet. Though the electron in the hydrogen atom is not a little speck or point or particle that is orbiting round about a nucleus, like a moon goes around a planet, nonetheless, the idea of angular momentum is still important in the proper quantum mechanical picture of an atom like hydrogen. Though Bohr's early proposal of his hydrogen atom model was not quite right, it did correctly identify that the quantization of angular momentum in units of h-bar was quite important. Before we start discussing the hydrogen atom then, we need to understand the angular momentum in quantum mechanics. Once we've done this, much of our understanding of the hydrogen atom will become quite straightforward. Linear momentum eigenfunctions are functions of position along a specific spatial direction. Angular momentum eigenfunctions are functions of angle or angles about a specific axis. So there are a couple of angles here that we could talk about. As a result of this, unlike linear momentum, angular momentum always has discrete eigenvalues. For eigenfunctions in space, this is associated with the fact that once we've gone an angle 2 pi around in a circle about a particular axis, we have to be back to where we started. The behavior of angular momentum operators is also somewhat more complicated than linear momentum operators, but the mathematics we've set up for operators will make it still relatively straightforward to deal with these angular momentum operators. So first of all, let's preview where we're going with angular momentum in quantum mechanics.
For our angular momentum, we're going to have operators corresponding to angular momentum about different orthogonal axes. So we'll have one for the x-axis, that will be Lx, and one for the y, and one for the z. But a strange thing about them is that they do not commute with one another. In general, these operators do not share eigenfunctions. And that's in contrast to what we're used to from linear momentum operators, for example, for the different coordinate directions. Px, Py, and Pz would all commute with one another. There is, however, another rather useful operator when thinking about angular momentum, and that one is called L squared. And that does commute separately with each of these operators, Lx or Ly or Lz. The eigenfunctions for Lx, Ly, and Lz are individually going to be quite simple. The ones for L squared are things called spherical harmonics, and on the face of it they look much more complicated. However, they can be understood relatively simply, and these are particularly important because they form the angular shapes of the hydrogen atom orbitals. So these spherical harmonics are at the root of all of the orbitals in atoms. So let's look at classical angular momentum first, and we'll build up towards how we're going to generate quantum versions of angular momentum operations. Here we're showing some axes, an x-axis and a y-axis, and we imagine we have some particle or object moving along like this, just a classical object, and at some position vector r, our object happens to be there, and we've got an angle theta between the direction the object is going and this position vector r. So we've got a momentum vector and a position vector for this object, and there's an angle theta involved with that. So the classical angular momentum of some small object of linear momentum p, that's this vector here, centered at some point, here's where the object is, that is given by a position vector, r, relative to the origin of our coordinates, is formally the cross product of the position vector and the momentum vector. And that's called a vector L, and that's a vector that will be in this direction perpendicular to x and y here. You might incidentally think it's a little odd to think of something that's going in a straight line as having angular momentum. You're perhaps more used to thinking of something that's going round in a circle as having angular momentum, and it certainly does. If it goes round in a circle here, this L equal to R cross P can be a good constant of the motion of the system. But it's also mathematically true, and physically as well, that a particle going in a straight line relative to some specific point or some origin does also have angular momentum. And classically, this angular momentum, you'll find if we check it out with the formula we're going to write down, it is also conserved even if the particle is just moving in a straight line when we're thinking about angular momentum relative to this origin. Anyway, we can write angular momentum in this form no matter what kind of motion we're actually thinking of. Now let's remind ourselves of the vector cross product operation. As usual, if we take two vectors, A and B, and multiply them in this order, A cross B, we can work out what that is. There are two formulas for doing that. One is this one involving the sine of the angle between these vectors. So this is a vector in a specific direction given by this unit vector C here, and A is the magnitude of vector A, and B is the magnitude of vector B, and sine theta is the angle between them. There's also another form directly in terms of the components of the vectors, and this could be, as we've written out in this long formula here, or if you remember how to work out determinants, this form here is a shorthand way of writing down everything that we see down here. And these i's, j's, and k's are unit vectors in the x, y, and z directions. So formally, ax is the component of the vector A in the x direction, and so on. And the components of B are similarly defined. Now, in this expression that we have here, formally C is perpendicular to the plane in which A and B lie, just as the z-axis is perpendicular to the plane containing the x and y axes, for example, in right-hand axes. And theta is just the angle between the vectors A and B, as we said. And C is a unit vector in the direction of the vector C. So that's in the direction perpendicular to the plane in which vectors A and B lie. Note that in this expression here, the order of the multiplications that we have chosen to write is rather careful, and it's always in the order moving from top row to middle row to bottom row. And we've chosen that explicitly in this expression that we have here because we're going to be working later on with operators, and the order in which we perform the multiplication, as it were, of operators is rather important because of the commutation or otherwise of operators. So the sequence of our multiplications in our cross product expression is always going to be from top to middle to bottom. With classical angular momentum, L equals R cross P, we can, if we want, write out the various components. So from our formula we were just working with, Lx, the component in the x direction of this vector cross product, would just be y times pz minus z times py. And similarly for the other two components, the component along the y direction and the component along the z direction. Now we are going to propose a quantum mechanical angular momentum operator, L, so we put a hat on it here, and we're going to base that on substituting in the position and momentum operators. So every time we have, say, the y-coordinate value in here, we would replace that by the operator for the y-coordinate. Now, because we're working in the position representation at the moment, it's not really very obvious that there's much difference between the coordinate y itself and the operator representing it. But in the case of the momentum operators, of course, we know that indeed we have quite a different expression here we're going to substitute for the quantum mechanical momentum operator in the z direction, and similarly in the y direction and in the x direction. So now our new operator for angular momentum is going to be the position operator, vector cross-producted into the momentum operator. And because we're in the position representation, this position operator and the position vector are the same thing. They're not in general in different representations. But certainly the p operator is a quantity that we know, minus IH bar times the gradient operator here. So this is going to be our proposed form of the angular momentum operator L. And we can similarly write out component operators Lx hat, Ly hat, and Lz hat if we want to. So analogously, we obtain these three operators. Here's the one for the x direction. It would be y hat, the y position operator, times pz hat, the z momentum operator, minus z hat, the z position operator, times py hat, the y momentum operator. Of course, writing that out, we get this expression here. And we can proceed similarly for the other two coordinate directions for the momentum operator, Ly here and Lz, with hats on each of these. And each of these operators we could check is Hermitian. And so correspondingly, the operator L itself is Hermitian because it's just a sum of three Hermitian operators. Now, these operators obey commutation relations, and I'm just going to state them here. Here's the commutation relation between Lx and Ly, for example, the commutator of Lx and Ly, and you'll find if you check that out, it's quite straightforward to do so, that it's IH bar times the Lz operator. And similarly, the commutator of Ly and Lz operators is IH bar times the Lx operator. And the commutator of the Lz and Lx operators is IH bar times the Ly operator. Now note, these commutators are telling us that in fact these operators are not going to be in general sharing the same sets of eigenfunctions because these operators do not commute. We can check that algebraically quite easily from the expressions we had just written down. And you can, if you want, write down these three commutation relations in one compact form. You could write the cross product of L operator and L operator is IH bar times the L operator. That's not an expression we use very much, by the way. We tend to work directly with these, but this is a shorthand way of writing down all three of these, and you can check that. Now, unlike position and momentum operators, the different components of this angular momentum operator, as I said, they do not commute with one another. Their commutators are not in general zero. And so this is telling us that though a particle can simultaneously have a well-defined position in both the x and y directions, for example, or simultaneously have well-defined momentum in both the x and y directions, a particle cannot in general simultaneously have a well-defined angular momentum component in more than one of these directions.